Hello and welcome everyone to the first of the A-Level Chemistry All Wales catch-up sessions. My name is Mr. Johnston and I'll be presenting the topic this afternoon. Okay, we also have Mr. Pickett in the background answering questions. Okay, so as I'm going through this topic, please do feel free to ask questions in the chat. Okay, and Mr. Pickett will be answering for you. So we're going to go straight into it. Okay, and we're going to start by having a quick look at what the content is today. So our session objectives today, we're going to look very briefly at electron transfer and oxidation states, which are the AS content for this particular topic. And then we're going to move swiftly into the A2 content on redox half equations, which involves splitting redox equations into multiple half equations. Elemental half equations, I've called it that because they just involve one particular element. Oxo half equations, which involve an element combined with oxygen. And combining half equations into full redox equations. And then from there, we're going to move on to electrical chemical cells and cell diagrams, and we're going to be calculating cell EMF. So moving swiftly on, little reminder about electron transfer. Okay, when we talk about oxidation in A-level, we're talking about electron loss. And when we talk about reduction, we're talking about electron gain. And there's a little reminder of the oil rig acronym there, just to remind you of that. Okay, so we're going to have a quick look at how electron transfer can be determined with the use of oxidation states. So a brief reminder of all of the rules about oxidation states. Okay, the oxidation state of all atoms in elements is 0. Okay, so I've put some examples there: chlorine, iron, sodium, oxygen. In neutral molecules, the overall oxidation state is equal to 0. Now, our example here is sulfur trioxide, SO3. Okay, oxygen has an oxidation state of -2, and that's one of the sort of harder, fast rules that we'll talk about in a second. So that means that sulfur must have an oxidation state of +6. So, and you can see there that overall SO3 has an oxidation state of 0. In ions, we're talking about complex ions here, the sum of the oxidation states must equal the charge on the ion. So I've got dichromate here. Okay, chromium has an oxidation state of +6, oxygen has an oxidation state of -2, and so we take 2 times 6, which is +12, add that to 7 times -2, which is -14, and we end up with an overall oxidation state of -2, which matches the charge. And these are some rules that can help you figure out oxidation states of more unusual elements. So group 1 metals always have an oxidation state of +1. Okay, group 2 always +2. I've singled out aluminium here for group 3 because group 3 doesn't always follow the +3 rule, but aluminium is the most common one you'll come across. Hydrogen is always +1, except for group 1 or 2 metal hydrides, where it is -1. Okay, so if you've got hydrogen joined to a group 1 or group 2 metal, its oxidation state is -1 instead of +1. Fluorine is always -1 under all circumstances. Oxygen is always -2, except in hydrogen peroxide, where it is -1, or when it's bonded to fluorine, and because fluorine is always -1, then the oxidation state of oxygen will be positive. And then chlorine is always -1, except when bonded to oxygen or fluorine, where it takes a positive oxidation state instead. So if we look at our oxidation and, one example of an oxidation and reduction equation, okay, then we can determine whether electrons are lost or gained. Okay, feel free to pause the video at this point if you're not watching this live, see if you can figure it out. But we start with our rules. So we know that oxygen is -2 because it's not in a peroxide and it's not bonded to fluorine. Iron must be +2 on the left-hand side because its ionic charge is +2, and hydrogen is +1. We also know that manganese in Mn2 plus must be +2 because it matches the charge. Fe3 plus +3, same reason. Hydrogen, again, is +1. That's one of our rules. Okay, it's not bonded to a group 1 or group 2 metal. And oxygen -2 again. The only unusual one really is the manganese in MnO4-. We have 4 oxygens, each with a -2 charge. That gives us a total of -8. We are aiming for a charge of -1, so the oxidation number must be +7. So this first one, okay, is oxidation, because the oxidation state has increased from +2 to +3. So if you're, thinking, well, which one is reduced? Well, we're looking for ones that have changed. We've gone from manganese +7 to manganese +2. So that one is reduction because the oxidation state has gone down. Okay, now I've used this example to show how to separate redox equations into 2 half equations. So the first step for this would be to write both species involved in the oxidation and reduction separately from each other. So we've already identified that Fe2 plus and Fe3 plus are involved in oxidation. So we just write those separately to the rest of the equation, which is MnO4- and Mn2+. I haven't done anything with the H plus and the H2O just yet, because we do that in the next step. Add any species associated with the oxidation and reduction. Now, the H plus and the H2O are associated with the MnO4- species because water contains oxygen, just like the permanganate ion does. And so the water must be part of that equation. And then, of course, H plus must be part of this equation as well to balance the hydrogens from the water. And then we balance the atoms and add electrons to balance the charges. So what I've done here for the oxidation step is I've cancelled it down. So we've gone from having 5 Fe2 plus and 5 Fe3 plus to just 1. Because both 5, they can cancel down to 1, and I've added an electron on the right hand side so that both sides add up to a total charge of +2. And again on on the reduction, okay, again looking at the charges, we had -1 and +8 pluses for a total of +7 on this side. On this side, on the left-hand side, it's just +2. So we need 5 electrons to balance that equation out and balance the charges there. So let's have a look at some elemental half equations. Okay, so 3 simple steps. Identify the oxidized and reduced species in the equation. Okay, balance the atoms and balance the charges with electrons. Now, I did want this to pop up one at a time so I could go through it. I apologize for that, bit of a technical issue there. But you can see that if we talk about the oxidation of aluminium, the reduced form is aluminium metal, the oxidized form is Al3+. Okay, balancing the atoms, there is no balancing to do for the oxidation example I've given here because we've got 1 Al on both sides. And notice how I've put atoms in quotation marks because obviously Al3+ is an ion, but we're not dealing with the charges until step 3. Step 3, we need 3 electrons to balance out the 3 positive charges on the right-hand side to make it neutral, just like on the left-hand side. Now, for a reduction example, okay, we took O2 and reducing it to oxide, O2-. This time we do need to balance the atoms in quotation marks because we have 2 oxygens on the left-hand side, but we only have 1 on the right-hand side at the moment. So we need to stick a 2 in front of the oxide. Then we bung in 4 electrons because we've got a total charge of -4, 2 times 2 on this side. So we need 4 electrons to balance that out. Right, now with the oxo equations, okay, we have 5 steps. Okay, and again, I wanted these to pop up one at a time, but never mind. Okay, so first we identify the oxidized and reduced species in the equation. Okay, so this was going to be oxidation of sulfide to sulfate. So I've isolated sulfide and sulfate into a single equation. Next, we balance the atoms, but not oxygen at this point. Okay, so in this case, we're balancing sulfur atoms, and there's nothing to do because there's one sulfur on the left, one sulfur on the right. Next, we balance any oxygen atoms with H2O molecules. Okay, so we have 4 oxygens on the right-hand side from SO4 2-. So we need 4 waters to balance out those oxygens. So we simply add 4 H2O into the equation on the left-hand side. Now, for step 4, we balance the hydrogen atoms from the water molecules with H+ ions on the other side. So we've added 4 water molecules on this side. We need 8 H+ to balance out those hydrogens. So we're almost there. Last step, we're going to balance out the charges by adding electrons where appropriate. So on this side, the left-hand side, we have 2- as our final charge, okay? And on this side, we have 2- and 8 pluses for a total of +6. So we need to add electrons on this side, and we need to add 8 so that we have a total of -2 on the right-hand side. Let's have a look at a slightly more complicated example to do with reduction. So we have our species here, dichromate to chromium-3, which I've just written out here. We do need to balance the atoms in step 2 because we have 2 chromium atoms in dichromate, but only 1 in chromium-3+, so we stick a 2 in front of Cr3+ there. Once we've done that, we balance out the oxygens with water, so we're adding water to the right-hand side, and we need 7 of them because we've got 7 oxygens to balance out. Once we've added 7 oxygens, we need 14 H+ to balance out those hydrogens. And then once we've done that, we need to balance out the charges. So on the right-hand side, the total charge is +6. It's 2 times 3+. And then on this side, we've got -2 from the dichromate, and we've got 14 pluses from the H+, the 14 H pluses. So we've got a total there of +12 on that side. So +12 on the right, +6 on the left. We need 6 negative charges to go into the right-hand side and make those charges balance. Okay. Right, now we're going to have a quick look at combining half equations. This is going to be really important. So once we've got our half equations, however we got them, okay, the first thing we need to do is write the 2 half equations out in full. Okay, and oh, I did again want that to appear, one at a time, but never mind. So here's 2 half equations I've selected. Okay, so this is the oxidation of vanadium 2+ to vanadium 3+, and this is the reduction of manganate 7 to manganese 2+. Okay, so we write those out in full. We don't worry about about matching them up yet, because what we need to do is in the second step, we multiply one or both of the half equations so that the number of electrons are equal in both half equations. So we have the oxidation equation has just 1 electron, whereas the reduction equation requires 5. So I have multiplied the oxidation half equation by 5, and I've multiplied everything in it by 5. That's really important, okay? Multiplied absolutely everything in there by 5. The blue equation, the reduction equation, doesn't need anything doing to it, okay? Then we combine the 2 half equations together. So I've kept the color coding so that you can see I've simply taken V2+, all 5 of them, and added them to the left-hand side of the permanganate half equation, and then I've done the same on the right-hand side. Okay, so nothing too bad there. And then we need to cancel out any electrons and any repeated species, such as H2O or H+. So if we've got H2O or H+ on both sides of the equation, then we need to cancel those out as well. Now, because we've prepared earlier in step 2 and we've got the number of electrons the same, the electrons just disappear from the equation completely. Okay, and there are no repeated species to cancel out in this example. So there's no, so basically everything stays as it was in step 3, apart from we've got rid of the electrons. Okay, so that's a relatively simple example there. Now, for the next example, a little bit more complicated. Okay, so I'm going to take the 2 equations I worked with earlier, the sulfide to sulfate and the dichromate to chromium 3+ that we worked through earlier, and combine those together. Now you can see that we've got 8 electrons for the oxidation equation and 6 for the reduction equation. Now, this is where your maths skills will come in, because what we're looking for here is the lowest common multiple of those 2 numbers. Okay, so the lowest common multiple. And in this case, as you've probably seen in step 2, the lowest common multiple of 8 and 6 is 24. So in order to get these balanced, I have to multiply the first equation, the oxidation equation in red, by 3. And then I have to multiply the blue equation, the reduction half equation, by 4. And that way we get 24 electrons for both half equations. Once we've done that, we combine them all together again. Okay, and this time not only have we got electrons on both sides, but now we've got H+ and water on both sides as well. Okay, so we need to look at cancelling these out. Well, we've got 12 waters on the left-hand side and 28 on the right. So we simply remove 12 H2Os from the right-hand side and remove them from the left-hand side completely, and we end up with 16 H2O molecules left on the right-hand side. As for the H+, we've got 24 on the right-hand side and 56 on the left. So we take away 24 from 56 and we end up with 32 H+. So our final answer here, 3S2- plus 4 Cr2O7 2- plus 32 H+, having cancelled some of those out, gives 3SO4 2- 8 Cr3 plus and 16 H2Os. Again, we've cancelled some of those out. So now that we've gone through the basics of splitting up and combining half equations, we're now going to have a look at the practical application of this, which is setting up electrochemical half cells. Now, the electrochemical half cells are basically where we combine a reduced form of a species with an oxidized form of a species, and there are 3 ways of doing that. Now, I will point out that these are not official names. Okay, these are just ways that I personally remember them, and you know, it's not an official name. So you know, please don't quote me on this in your exam. But the first type is what I call the metal electrode, because it involves the metal you know, that you're actually investigating. So in my diagrams, I've got iron and copper. Okay, now for the iron half cell, we combine iron metal with iron in its oxidized form. In this case, it's Fe2+. So we just dip a piece of iron into a solution of Fe2+. Okay, in this case, iron 2 sulfate. Okay, the iron will act as the electrode, which is the interface between the half cell and the rest of the circuit. Okay, so that's what we've got. We've got the electrode made of elemental metal dipped into a solution of aqueous metal ions. The solution has to have a concentration of 1 mole per dm cubed. That is really, really important. That is part of what makes it standard. Okay. The other part that makes this standard is that it must be at a temperature of 298 kelvins, okay, which is our standard room temperature. So that is what I consider to be the simplest half cell. Okay, the next one is the gas electrode. Okay, now this is a little bit more complicated. Okay, so the example I've got here on my little diagram is hydrogen gas being pumped into a glass tube. Okay, which has a platinum electrode at the bottom, and the idea is the platinum electrode is in contact with both the solution and the gas. Okay, so it's the platinum that is acting as the interface between the gas and the solution in this case. Okay, the reason platinum is chosen is twofold really. First of all, it is a very good conductor of electricity, but more importantly, it is chemically inert. It is unlikely to react with whatever you're testing. Okay, it's not completely unreactive, but it's so unreactive that it's unlikely to react with anything you put it through. So the gas is passed over the platinum electrode, which is also in contact with the solution of ions. Again, the solution must have a concentration of 1 mole per dm cubed, so that's the same as in the previous example. Now, to make this one standard, we must also have a pressure of gas at 1 atmosphere, which is 1.01 times 10 to the 5 pascals. And the half cell must be at the temperature of 298 Kelvin. So again, pretty standard there. And finally, this one I've called the aqueous electrode, okay, because both the reduced and oxidized forms are in solution, okay. So a platinum electrode is dipped into a solution containing ions of both ions involved in the redox process. Now, the example I've given here is 2 vanadium containing ions, okay, VO2 plus and VO2 plus, okay. So these two are both in solution, and you're oxidizing or reducing these ions from one into the other. Okay, the platinum electrode is not involved in the redox at all. It just acts as an interface between the circuit and the solution. Okay, so the solution has to have a concentration of 1 mole per dm cubed of both ions. Okay, so you need to have the concentration of both at 1 mole per dm cubed, and the half cell must have a temperature of 298 Kelvin. Again, hopefully you're seeing a pattern here. So when we set these half cells up into a full electrochemical cell, we connect, basically, if you've drawn this out, okay, with one on the left and one on the right, okay, this is how to do it so that you basically avoid confusion, so that the calculations that you do in these experiments make sense. You take the left-hand electrode, the left-hand half cell, and you connect that to the positive terminal of the voltmeter. So left-hand electrode to the positive terminal. You then connect the right-hand electrode to the negative terminal. That almost goes without saying, but I put it in there anyway. And then we connect the 2 half cells using a salt bridge. If you had the chance to do this experiment before we were all sent home, then you probably used filter paper dipped in saturated potassium nitrate solution. Potassium nitrate is selected because it's unlikely to form any precipitates with any of the other solutions that you could be using, because potassium salts are all soluble and nitrate salts are pretty much all soluble as well. So that's why potassium nitrate is used. So if this cell is set up correctly, so that you've got your left-hand electrode connected to the positive terminal, then a positive cell EMF means that the left-hand cell will undergo oxidation and the right-hand half cell will undergo reduction. Okay, that's if you've set it up the way that I've suggested. Okay, if the cell EMF is negative, then the opposite reactions occur. So the left-hand cell will undergo reduction and the right-hand cell will undergo oxidation. Okay, so that's why I think it's really important to make sure you know how you're setting these up, because if you set them up the same way each time, then the readings you get will be far easier to interpret. So, cell diagrams. Cell diagram is basically a shorthand representation of an electrochemical cell. Okay, so we write the oxidation on the left-hand side, reduction on the right, must include state symbols, uses a single vertical line to represent a phase boundary where the state of matter changes, and it uses a double vertical line to represent the salt bridge, and uses a comma to separate different chemical species that are in the same state, usually aqueous. So if I move on to examples here, okay, for this particular example, we have got a metal half cell with a piece of zinc metal dipped into zinc solution, okay, connected to copper dipped in copper solution. The way that we would write this out, because we're assuming that zinc undergoes oxidation in this case, we would write it out like this. Okay, zinc solid, okay, single straight line, vertical line between the solid zinc metal and the aqueous zinc 2 plus ions. Okay, so that is a phase boundary because there is a change in state going from solid to aqueous. We then have a double vertical straight line to indicate the salt bridge, and then the reduction goes on the other side. So we start with the oxidized form, which is copper 2 plus in the aqueous phase, and then single vertical line, and then we have the reduced form, which is the copper metal, so Cu solid. Okay, so that's one example. Both of those, including the metal electrodes, as I call them. Now, what I've got here is a combination of my my gas electrode that I used earlier, okay, which has hydrogen in it, okay, and the aqueous electrode, which has these vanadium species in. So we've got our oxidation again on the left-hand side. So we start with our reduced form and we end with our oxidized form. So H2 gas going to H plus aqueous. But what we need as well for these electrodes is we need to include the platinum, because the platinum is involved in the electron transfer because it allows the gas and the solution to interface. So what we start off with is platinum solid, okay, then we have our phase boundary, then we have hydrogen gas, which is our reduced form of the left-hand side, then another phase boundary, then H plus aqueous, which is our oxidized form, then we have our salt bridge. Now for the aqueous electrode, we have both of our species, both the oxidized form, which is closer to the salt bridge, and the reduced form in the aqueous phase. So rather than separating them with a phase boundary, rather than separating them with the line, we separate them with a comma to show that they are in the same phase. But then, of course, we have a platinum electrode in this, so we need to have a phase boundary and then end with a platinum electrode. So with these gas electrodes and aqueous electrodes, we always either start or end with a platinum electrode. So it always starts or ends with PT in the solid state. Okay. Now, the hydrogen gas electrode is a bit special, okay, because it's, well, I say it's a bit special. It is a gas electrode with hydrogen going through it, okay? So hydrogen gas is passed over the platinum electrode, which is in contact with an aqueous solution of hydrogen ions, usually in the form of sulfuric acid, okay? But as long as it has H plus ions in there, doesn't matter too much, really. The solution must have a concentration of 1 mole per dm cubed of hydrogen ions. Okay, now that's really important because if you have a diprotic acid like sulfuric acid, that releases 2 H plus ions for every acid molecule. So you would need to have half a mole per dm cubed of sulfuric acid to get that. Okay, the 1 mole per dm cubed has to be hydrogen ions. Hydrogen gas must be at pressure of 1 atmosphere. That's, you know, same as the gas electrode. Half cell must be at a temperature of 298 K. Again, that's the same, but this is the important bit for the standard hydrogen electrode. It is arbitrarily given an electrode potential of 0 volts. So we just say, right, okay, that particular half cell, that has an electrode potential of 0. That means we can compare every other half cell that we have to that one. Okay, so we can just, you know, compare them, and, you know, then by having a standard, you know, electrode with a potential of 0, we then start to put together a series of standard reduction potentials. By putting the standard hydrogen electrode on the left, connected to the positive terminal of the voltmeter, and the half cell being tested on the right, that means that we're going to test every single half cell fairly, and we can compare them all to each other. Okay, so we're trying to reduce the half cell that is on the right. Okay, so the one that we're testing. That's why this is called the standard reduction potential. Okay, because we're trying to reduce them. Now, when we get our table out, anything that is positive on this table, they all undergo reduction with respect to hydrogen. So that means that they're likely to be good oxidizing agents. Okay, I say likely. Okay, obviously the higher these values, the better oxidizing agent they're going to be, which of course means that if you've got a negative value compared to hydrogen, that means that you're going to have them oxidized by hydrogen, and so they're likely to be good reducing agents. Okay, but these values are, you know, they're not used to determine whether something is an oxidizing agent or reducing agent, although you can see, you know, that it can be used for that purpose from this particular slide, but it's more likely used to calculate the cell EMF. So when we connect two half cells together that aren't the standard hydrogen electrode, we can work out the expected cell EMF. Okay, so to calculate the cell EMF when connecting two half cells, we've got this formula. Now, I apologize, the standard symbol isn't quite right, but I don't have access to it on PowerPoint. We take the standard reduction potential of the species you're trying to reduce, okay, and then we subtract the standard reduction potential of the species you're trying to oxidize. Now, in terms of the experimental setup we used earlier, that means that you essentially take the standard reduction potential of the species on the right-hand side of the cell, and then subtract the standard reduction potential of the left-hand side from it. Okay, so it boils down to right-hand side, take away left-hand side. That is assuming that you followed all the correct setup guidelines. So, you know, connecting the oxidized one to the positive terminal on the voltmeter, etc., etc. So if we have a quick look at how to calculate these cell EMF values. Okay, we've got iron to iron 2 plus half cell on the left, and the copper 2 plus half cell on the right. So I've put the standard reduction potentials here. Okay, and when we go through the calculation, okay, here's a recap. Okay, it's the reduced species minus the oxidized species, or right minus left, and that's what we get. Okay, so we take 0.34, which is the right-hand side, and we subtract the value for the left-hand side. And because we've got a minus-minus situation, that becomes positive. We end up with a value of 0.79 volts, which means that this cell EMF is positive, so iron will be oxidized to iron 2 plus, and copper 2 ions will be reduced back to copper metal. Okay, so that one worked out really well there. Okay, we put it the right way around. Now, using a cell diagram, very similar to using an actual diagram or an experiment, where we simply take the oxidized side. Remember, the oxidized side is on the left, and then the reduced side is on the right. Okay. Oh, I apologize. There is a mistake there. That value is actually correct for aluminium. I've just forgotten to change that. I apologize for that. Okay, so if we do the same, so this one should read Al3 plus / Al. Okay, that's minus 1.66. So that is our right-hand side. So it's right-hand side, take away left-hand side. We end up with minus 1.66 minus 0.13, and we end up with a negative value from this one. Okay, so the cell EMF is negative. This means that lead-2 ions would be reduced. So the left-hand side would actually undergo reduction, and the aluminium would be oxidized. And that is opposite to how the cell diagram is written, because we've ended up with a negative value. Okay, and a word problem. So determine if adding cadmium metal to a solution of zinc ions would result in a displacement reaction. Okay, so this time, rather than working with electrochemical cells, this time we're going to use electrochemical data to figure out whether or not cadmium will be oxidized while zinc ions are being reduced. Okay, because we're starting with cadmium metal, we must be oxidizing cadmium. Okay, because we've been given, we've been told it's cadmium 2+, and we must be trying to reduce the zinc 2+ ions back down to zinc metal. So if we're trying to oxidize cadmium and reduce zinc 2+, okay, then basically we have zinc being reduced. So we start with minus 0.76, which is our value here, and then we subtract minus 0.40 from that, because that's what we're trying to oxidize. And that's what we get. So we get minus 0.76 minus 0.40, and we end up with minus 0.36 volts. Now, because that is a negative value, that means that this would not work. Okay, this reaction, adding cadmium metal to try and reduce zinc ions back to zinc metal, would not work. However, if we did it the other way around, where we added zinc metal to a solution of cadmium ions, then it would result in displacement. We would form cadmium metal, and the zinc would be oxidized to zinc 2+. Okay. Right, okay, at this point, we've only got 3 minutes left, and I do have some more slides about redox titrations, but I know that, well, we've only got 2 minutes left now. So what I'm going to do is I'm going to quickly cycle through the slides that I've got on redox titrations so that you can, read through them for yourself, and hopefully they will be of use to you. Okay. I don't have time to talk through every single one. So I have put the instructions in the corner of each of these slides. So I go through some examples here of how to do, redox titrations, and I've stuck to my red is oxidation, blue is reduction color scheme. Okay, so if you're watching this recorded, please feel free to pause and look through the calculations. So that's the first calculation, second calculation. Now with this one, I've had to split it over multiple slides. So this one is the formation, sorry, that one was the formation of the half equations. You need 2 of them for this particular one. So again, repeating the question. Now that we've got that, we can calculate moles. I'm sorry, I'll go back to that one. Then calculating once we've got moles of that. So there we go. I've just spotted a mistake as well. It's meant to be SO2 O32 minus on the first line of 0.3. My apologies. And then final slide, like so. Okay, so there is the final answer for that particular one. Again, feel free to pause. Now, last slide, I've included some useful links that relate to this particular topic. We've got experiments on film. Experiments 13, 14, and 15 relate to the work that I was going through today. And the WJC resources have recently been updated. Okay, there is a really good revision guide on there, and there's now topic by topic blended learning resources that you can look at as well. And I'd just like to say thank you for listening. Okay, it's been a privilege to be on here helping you guys. Next week it will be me again presenting, and I'm going to be going through topics 8 and 9, which is equilibria and acid-base equilibria. So thank you very much for your time and for your attention, and take care of yourselves. Bye-bye.